In high school, I learned that physical quantities are either scalars, like temperature, which is just a number, or vectors, like velocity, which is a number and a direction. But there's a far more powerful mathematical object that shows up everywhere, from engineering to material science and even astronomy. It's called a tensor. To be specific, rank 2 and higher tensors. But here's a question. What the heck is a tensor? Most definitions I read were pretty vague, and then I learned that it is kind of like a matrix, but it's better to think in terms of indices. Yeah, none of that made any intuitive sense to me until now. I went through the entire lesson on tensors by Feynman lectures, and although he has not even defined even once what tensor is in the entire chapter, by the end of it, it all clicked, and oh my god, my mind was blown. So the goal of this video is we're going to pretend we don't know anything about tensors and start from scratch and step by step intuitively rediscover all these ideas ourselves. And if I do this right, we might even be able to intuitively understand why some of the most complex equations of physics, like the Einstein's field equations of general relativity, has to be written in the language of higher order tensors, not just vectors. All right. So if you're ready for this, let's begin. So Feynman, where do we start? Feynman says, Mahesh, let's start with a very familiar problem, Ohm's law. And I'm like, that's awesome. I love Ohm's law. It states that current through a wire will always be proportional to the voltage across it, which means the current I is proportional to voltage V. But Feynman says, Mahesh, let's look at the vector version. In that, instead of current, we use current density J, which is basically current per unit area. And instead of voltage, we have electric field. So we get J proportional to E. We obviously won't show that it's the same form as I proportional to V, but it makes intuitive sense, right? I mean, through an area, if you put a stronger electric field, the electrons over there will experience a stronger force. They will drift faster, giving you a stronger current. So it makes sense, right? And the proportionality constant over here is called conductivity. It's a measure of how good a conductor a material is. If the number is higher, it's a better conductor. But now, Feynman asks me a question, the central question of this entire video. You ready? He asks, Mahesh, how many numbers do you need to fully describe conductivity? I'm like, one. You just need one number, right? I mean, if the conductivity is 3 units, for example, it means there will be 3 units of current density per unit electric field. So Feynman, you just need one number. And Feynman smirks and says, Mahesh, that would be true if the conducting property was the same in all the direction. But what if you have a crystal like graphite, which conducts very nicely along its layers, but it conducts very poorly across the layers? Conductivity in graphite depends on the direction. We call them anisotropic crystals. So what if you have an anisotropic crystal over here, and for simplicity, let's say along the horizontal, the material conducts very well. But let's say along the vertical, it doesn't conduct at all. So put an electric field along the horizontal, you get nice current density, but you put an electric field along the vertical, you get nothing. Now, Mahesh, do you think one number is enough to fully describe conductivity in such a material? I'm like, ooh, interesting. This is getting complicated, but nothing we cannot handle. I mean, we can think in terms of components, right? So here's what I say. All right, let's use 2 numbers, one for X and one for Y. So in this case, for example, along the X, the conductivity might be 3 units, but along the Y, the conductivity would be 0. So I stand corrected, Feynman. You're right. I need 2 numbers to fully represent conductivity, and that is in 2 dimensions. Of course, if we're in 3 dimensions, we have 3 axes. So we would need 3 numbers to fully represent conductivity in general in such anisotropic crystals. But Feynman asks, Mahesh, are you sure? Okay, let's double check. What if we put an electric field in some arbitrary direction? Are these 2 numbers enough to fully calculate the current density in this material? Let's see. If I were to decompose the electric field along the X and Y direction, I can now use this number to calculate the current density along the X direction. And then I can use this number to calculate the current density along the Y direction. In this case, it's 0. And then I can add those 2 together vectorially to find the total current density. And I can do this for any arbitrary direction of electric field. So yes, Feynman, I am sure. I need only 2 numbers in 2D, of course, 3 numbers in 3D to fully represent conductivity in any material. But Feynman says, Mahesh, nope, you need more numbers. Here, you just got lucky. What do you mean? Feynman says, Mahesh, for a second, forget about coordinate axis and everything and just look at what we got. We see that even though the current density is proportional to electric field, they are not in the same direction. And I'm like, that is interesting because till now, every single vector equation I have seen, the left-hand side vector was exactly in the same direction as the right-hand side vector. For example, consider F equals ma. F and a will always be in the same direction. P equals mv, where P is the momentum, V is the velocity. P and V always in the same direction. And so now for the very first time in my life, I am seeing an equation, a vector equation in which the left-hand side vector and the right-hand side vector are not aligned. That is truly interesting, Feynman. Thank you for noting that. But it still does not explain why you said I got lucky. So here's what Feynman says, all right? This is the interesting part, okay? So in general, in this particular crystal, electric field and current density are not aligned, isn't it? But along the horizontal, they are aligned. That is a special case. And we chose our x-axis to be in that special direction. Similarly, along the y direction, when you put an electric field, you get no current density. That's another special case over here. And our y-axis just happened to be along that direction. So Feynman says, Mahesh, do you see what has happened? We accidentally chose our coordinate axes to align with these very special cases. That's why things got super simplified and it feels like only two numbers are enough. But if you want to analyze this in general, we have to take an arbitrary coordinate axis. So what say we rotate the coordinate axis to some arbitrary angle and then reanalyze situation? I'm like, ooh, that is interesting. Very interesting. Let's do this. So let's rotate this coordinate axis and align it with some arbitrary direction. Let's align it with this electric field direction itself. So this is our x and this is our y. And Feynman says, look, Mahesh, look. Now, even though the electric field is along the x-axis, the current density is not aligned. So do you think one number, sigma x, is enough to calculate how much current density you get? What do you think? This is it, folks. This is the moment. Please, please pause, really pause and try to answer that question. How many numbers do you need to calculate current density due to the electric field in just the x direction? Try to figure this out yourself because this is the moment to rediscover it. I promise you it's the best feeling that you will get. It's the best way to learn. And it's one of the reasons why I love Brilliant, who's sponsoring this video. Why do I recommend Brilliant? Because just like in this particular video, it helps you intuitively rediscover ideas using a hands-on approach, but not just in math or physics, also in programming, data, and even AI. And you can get started for free. Take their course on vectors, for example. It starts off like a puzzle, and then using concrete interactive examples, you start visualizing things. And pretty soon you'll start mastering all the basic operations, transformations, and eventually you even start applying it. And because they have bite-sized lessons, you can learn on the go and level up even with 15 to 20 minutes a day. I have been urging my students to use Brilliant from way before they started sponsoring me. So you can try everything that Brilliant has to offer for free for a full 30 days by going to www.brilliant.org/FloatHeadPhysics. The link is also in the description, or you can just scan this QR code somewhere. And of course, you also get a 20% off on their annual premium subscription if you choose to buy it. Okay, back to the video. So how do we represent conductivity now? J is not aligned along E. We can decompose J along the X and Y direction, giving us Jx and Jy. So this means, look, the electric field component along the X direction gives us both Jx and Jy. It gives us two components of current density. This is the key. And therefore, I would need two numbers. One number to represent how much I get Jx due to Ex. So we can write it this way. But I also need another number to calculate how much I get Jy from Ex. So look, I need two numbers over here. And earlier, Because J was aligned along EX, there was only JX, there was no JY. That's why we missed it. That's why that number was 0 and it was hiding. This is what Feynman meant when he said, I got lucky. We didn't see it. So we need two numbers just to calculate J from EX. And the same thing, of course, applies to the Y component of the electric field here as well. We need two numbers to calculate J. One number to tell us how much you get Jx from EY, and another number to tell us how much we get Jy from EY. So look, in total, we need 4 numbers to fully describe conductivity, not 2, 4. And by the way, this itself took me some time to wrap my head around it because a lot is going on over here. So at first, if you don't get it, please don't be disheartened. This is not easy stuff. Mull over it, it'll make sense. But the whole idea of why we need 4 numbers is if I want to calculate Jx, I need to add contributions from both Ex and Ey. That's why I need 2 numbers for Jx, and similarly, I need 2 numbers for Jy, and that's why I need total of 4 numbers, not 2. But wait a second, do you see what I'm seeing? This looks like matrix multiplication. If we write it nicely in terms of matrix, it's a perfect matrix multiplication. Oh, this is why we write conductivity as matrix. It makes perfect sense now. But now Feynman asks, Mahesh, this is in 2 dimensions. How many numbers would you need for 3 dimensions? Again, great idea to pause and try to do this in your head. We have 3 components of current density to calculate, but for each component of current density, we need 3 numbers because there are 3 contributions that we need to add. And therefore, we need 3 times 3, 9 numbers. And that's exactly what we see. In 3 dimensions, we need 9 numbers to fully represent conductivity. And now we can do what mathematicians love to do, abstract the hell out of it. What about in n dimensions? Never mind what those n dimensions are, but how many numbers would we need if we had n dimensions? Now I have n components to calculate, but for each of them, I need n numbers to add up their contributions, which means I need a total of n square numbers. So there we have it. Conductivity in its full glory is a mathematical object that requires n square numbers in n dimensions. But Feynman, what do we call this thing? And are there other physical quantities like this? Well, Feynman says, Mahesh, think of it this way. Remember scalars like energy and mass? You think of them as something that only has magnitude, one number, right? But think of it this way. Regardless of the number of dimensions, you always need one number to represent a scalar, which means we could say that scalars require n to the power 0 numbers, where n is the number of dimensions, right? Okay. Similarly, think about vectors. You might think of vectors as something that has magnitude and direction, but another way to think about it is in terms of the fact that a vector requires 2 numbers in 2D, 1 for each component, 3 numbers in 3D. So in n dimensions, it requires n numbers. In other words, in n dimensions, it requires n power 1 numbers. And so from that, we can see conductivity is just an extension of that. Oh my God, this is it. This is why it actually makes sense to club them all together and under a same bucket and call them all something. We call them tensors. And so scalars are just rank 0 tensors. Vectors are rank 1 tensors. And so we're going to call conductivity as rank 2 tensors. But of course, our next question is, are there more quantities that are rank 2 tensors, and how do we again rediscover them? Feynman says, Mahesh, if you go back, what made conductivity a rank 2 tensor in the first place? Well, it all boiled down to one and only one thing. The J was proportional to E, but not necessarily aligned. If it was always in the same direction, conductivity would have been a scalar. But the fact that it's not necessarily always aligned forced conductivity to be a rank 2 tensor. So the next natural question for us is, are there other places where you have vectors proportional to each other but not necessarily aligned? Well, If you look at, say, a satellite going around the Earth, you probably know that it has some momentum, and momentum is mass times velocity. But when it comes to momentum, momentum and velocity are always aligned. They're always in the same direction, which is the reason why mass is a scalar, okay? But what about its rotational versions? You can write rotational momentum or angular momentum equals rotational inertia times angular velocity. Now, is angular velocity, angular momentum and angular velocity also always aligned? Let's see. You can spin them in multiple directions. For example, you can spin a satellite this way, or you can spin a satellite that way. And the key thing is that moment of inertia is not the same along along these directions. Moment of inertia changes with the axis of rotation. Okay? Therefore, even if the satellite was spinning with the exact same angular velocity in both these directions, because the moment of inertia are different, the angular momentum would be different. In one case, it will be higher. In the other case, it will be lower. Which means if you add them up together, look, the angular momentum will not be in the same direction as angular velocity in general. This means, boom, moment of inertia has to be a rank 2 tensor. I mean, right now, I don't really have the mental capacity to actually go through it and work out all the components, but it's the same as J and E. The fact that they're not aligned means the proportionality constant has to be a rank 2 tensor. Isn't that amazing? Next up, look at this dam. There are a ton of forces that are acting on it. But if you take a cross-sectional area, then in general, if this area is small enough, the force acting on a cross-sectional area can be written to be proportional to the area. That makes sense, right? Bigger the area, more the forces. And the proportionality constant is called the stress. Now comes the big question. Are forces and area always aligned? Well, let's see. Well, area is always perpendicular to the surface that we choose. And what about the net force? Well, there are multiple forces acting over here, so the net force can be in any direction, right? It depends on the context and what and all are forcing it. So clearly, force and area, net force and area need not be in the same direction, and therefore, boom, stress has to be a rank 2 tensor. The same idea. So look, we have so many examples of rank 2 tensors. We have conductivity, moment of inertia, stress, and so on. They all follow the same pattern. They map two vectors. They're proportional to each other, but they're not necessarily aligned in general. They have to be a rank 2 tensor. But let's not stop here. Let's go one step further. Feynman, can we intuitively think about even higher rank tensors like rank 3 and rank 4? Where would they appear? Well, when you squeeze certain crystals, charges get separated, producing an electric field. We are literally squeezing electricity out of crystals. We call this effect the piezoelectric effect. And to a good degree, the electric field generated is proportional to how much you squeeze it, or proportional to how much stress you're putting on this. So we can write electric field is proportional to the stress applied, and of course the proportionality constant is called the piezoelectric constant. But now think about this. Look at this equation. On the left hand side you have a vector which is a rank 1 tensor, but on the right hand side you have a rank 2 tensor. We just saw stress is a rank 2 tensor. So for the very first time I'm now looking at an equation that maps a rank 2 tensor to a rank 1 tensor, or a vector. And so now, what kind of an object should piezoelectric constant should be? Think about it. It needs to take in n square values, and for each of those n square values spit out n values, meaning it needs n to the power 3 numbers to fully represent it in n dimensions. Piezoelectric constant is a rank 3 tensor. And we can go even further if we think about elasticity. You probably know for any material, the deformation produced depends on how much stress you put on it. In other words, the strain is proportional to the stress you put. And again, the proportionality constant this time is the elastic constant. And guess what? Just like stress, strain is also a rank 2 tensor. Meaning in this equation, we are mapping one rank 2 tensor to another rank 2 tensor. So the proportionality constant over here, it needs to take in n square inputs, and for each input, it needs to spit out n square values of strain. So this would be a rank 4 tensor beast. Look, at this point, I have absolutely no mental capacity to dig into any of this in detail, okay? But what's interesting is that even without defining tensors, we haven't even defined what tensors are, we haven't talked about its notations or anything like that, just from raw intuition, we are able to rediscover all these amazing ideas. And that's what I find fascinating about Feynman's approach. Amazing, Feynman. Take a bow. But now I think it's time to finally answer our central question. What the heck is a tensor? Can we define it? Yes, we can. You can think of tensor as a machine that takes in one vector or a tensor and outputs another vector or a tensor. And the rank of this machine depends on the ranks of the input and the output. But it's not just any machine, it's not just any function. It follows two powerful rules. The first one is that the output should not depend on how you draw your coordinate axis. I mean, if you change the coordinate axis, the tensor components will change, but it should change in such a way that the output should remain the same. You should get the same output for the given input, right? Because nature does not care how you draw your lines. And second, we noticed something across all our examples. We had proportionalities. So it was a linear relationship, but not with just one number, but with multiple components. That's what a tensor is. It gives you linear relationships between multiple components, a multilinear machine. So putting it all together, tensors are multilinear machines that relate one tensor or a vector to another tensor or a vector. And the output is independent of how you choose to draw your coordinate axes. Finally, can we now use everything that we've learned to answer why Einstein's field equations must use tensors? Well, think about how could you encode space-time curvature. Well, here's the way to think about it. If I move a little bit along the x direction, for example, I need to think about how much the space stretches or squeezes in the y direction. But I should also think about how much the space stretches or squeezes in the z direction independently. It can also stretch and squeeze in the time direction, which of course I haven't shown over here. So look, for each component, each direction that I'm moving, I need multiple numbers to take care of curvature. In other words, I definitely need a tensor. That's why equations of general relativity involving space-time curvature require tensors. In fact, they use rank 2 tensors. But the last thing I want to say over here is that we have barely scratched the surface. This is just one way to think about tensors. There's just so much more to talk about. And there's so much more to explore when it comes to space-time curvature, like Ricci tensor, the metric tensor, Einstein's tensor, and even the rank 4 beast, the Riemann curvature tensor. And I think we can intuitively figure all of this out. So let me know if you want to get into all of that interesting stuff. I'll make future videos on that. So that's it.